This video is about SystemVerilog built-in data type, nets and variables. When you define a signal in SystemVerilog, it has two main characteristics, data type and types. Data type can be nets and variables. Nets are like physical connection. They connect source to destination. Variables can be physical connections like nets or also can be registers. It depends how they are defined in the code. Types can be two-state and four-state. Two-state means it accepts 0 and 1. And four-state, it means that it can be 0, 1, high impedance, and unknown. The keyword logic defines the variable or net that they are four-state. And a keyword bit defines variables that they are two-state. So variables can be two-state or four-state data type, but net can only be four-state data type. This slide summarizes the net properties. Net don't store value. It represents the current value of their driver. They can have multiple driver, and net type must be logic. Also, if you have undefined signal in your code, in your RTL code, the tools will infer it as a net type. Okay, we can use wire and try keyword to define net. Both of these keyword has same meaning. But it is recommended that if you have a try set value in your design, for example, you have 0, 1 and high impedance, it is more clear to define the net by using the try keyword. But but actually, these two keywords are exactly equal. Nets, declaration and assignment. There is two ways to declare and assign nets. First, implicit continuous assignment. So in the first line, we define a 32-bit packed vector data by using wire logic. And then we use the assign keyword to assign an expression or value to the data. Another way is implicit continuous assignment. In this way, we omit the assign keyword and we merge these two lines into one line. So simply we can use wire logic, 32-bit data is equal to A multiplied by B. These two assignments are equivalent and there is no difference. Net has two limitations. First, nets, for example, wire cannot have subfield. Consider this example where we define a two-dimensional data. This the second 7 to down to 0 make the data 8 to a two-dimension array. And the tools throw an error. A net is not a logical L value in this context. So it means that the two-dimensional array or subfield is not supported for the wire, and SystemVerilog only supports subfield for the variable. The solution is that remove the wire keyword to make the data a variable. The next net array limitation is that nets must be packed array. It couldn't be unpacked array. So consider this example. Here the first 7 to 0 define the number of bits, and the second one define array of 8 bits. This second 7 down to 0 make the array unpacked, and also unpacked array is not supported for the net in SystemVerilog, and as the previous one you get the same error. Also, the solution to this problem is that you remove the wire keyword to make the data 8 a variable. Variables. The left-hand side of always belong must be variables. You can define a variable, a four-state variable by using var logic keyword, and a two-state variable by using var bit keyword. Okay, always use four-state logic in your RTL code. Don't use two-state bit in the RTL design. There is one exception for loop iterator variables. I mean, by index in the for loop, you can use the bit. Why it is recommended to use four-state logic? Because the four-state logic can also accept the x value or unknown value. The x value shows a potential bug or a mismatch between synthesis and simulation in your design. So if you use the bit, the x value is automatically converted to 0 and 1, and it probably hide the potential bug, which is not good for your RTL code. So always use logic in your RTL code. These tables summarize the synthesizable variable data type in SystemVerilog. In Verilog, we have a reg data type, which is obsolete in SystemVerilog, and it's not recommended to use that. Equivalent to this keyword is var logic. Also, you can use integer. Integer is 32-bit variable, which is four-state and sign. Also, we have byte, which is 8-bit, short int, 16-bit, int 32-bit, and long int 64-bit variables. All of them are two-state sign variable. The difference between int and integer is that integer is four-state, but int is two-state variable. So again, use two-state data type for a validation and test bench. Don't use them in the RTL code. Logic data type. If you use logic alone, it usually interprets as var logic, except on input or in-out port, where logic is interpreted as wire logic. When you define a logic to connect multiple modules together, the tools interpret var logic. So be careful that variables don't support multiple driver. If in your design you have a tri-state bus, so 0, 1, and high impedance, define signal as wire logic or tri logic to support multiple driver functionality. In summary, always use logic data type, and only for connecting a multi-driven input or a tri-state bus, use wire logic or tri logic. So it means that you never need to use wire keyword, whether you use it logic or wire logic. Logic or var logic declaration and assignment. So by using a logic A, you define a 1-bit unsigned variable. And logic 31 down to 0, you define a 32-bit vector, a little endian. Or 0 up to 31, you define a 32-bit vector, a big endian. Because you don't use the signed keyword, all of these declarations are unsigned. To make your signal sign, you should use signed keyword. So in this example, logic sign 15 down to 0, data underline SN, you define a 6-bit sign variable. Fixed bit select and range select. If you assign a data underline LE to bus, it assign the 32-bit value of data to the bus. If you want to assign the bit number 5 of data underline BE to signal A, you use this line of the code. And to assign a range, for example, from bit 15 to bit 8, you use this line of the code. Be careful that because we define data underline LE as little endian, it means 31 down to 0, we couldn't use 8 up to 15. This is wrong, and we should use 15 down to 8, like this example. Another important thing is that the result of bit select and range select is always unsigned. Variable bit select. So in this example, the bit location A is assigned to bus bit 0. Because A can be a variable, this is variable bit select. Also, SystemVerilog support variable range select. The syntax for variable range select is shown here. Start shows the start bit, then plus shows that it's going upward, minus shows that it's going downward, and width shows the number of the bit. So this syntax is translated to the syntax shown here. So consider this example. We want 8 bits, which start from bit 15 and going downward. So it is equal to 15 down to 8.